Hello, good morning. It's a beautiful day, a little dusty, but hopefully it will be fine today, inshallah. We will start, as you know, all of our course references, notes on model. Also, there is a lot of verbs that will help you out through the slides, which is very, very important. Also, for the recorded lectures, you will find them all on the YouTube channel as you know. Today, I will start with the pre-optimization part. It's very, very important. It's handling all the tools that we will need down the road in order to understand the idea behind optimization. I will talk first about quadratic forms in specific. As when you do optimization, you are in between maximizing and minimizing, as you will see down the road. So if we are maximizing something, it means that you will have a crown in order to get a maximum point within the neighborhood of its domain. If you are minimizing, it means you are searching for a point which is the lower point with respect to the points in the neighborhood. So in both cases, we are searching for a point that's going to be relative to a quadratic form, as you can see. Okay. So the first part about the quadratic forms is to find the quadratic part in a polynomial. The quadratic part in a polynomial, we mean by the parts in the polynomial that have power 2, which may appear like x1 for a 2 for a quadratic general form of a function. You will find x1 to the power of 2, x2 to the power of 2, x3 to the power of 2, up to xn to the power of 2. So the quadratic idea, it's coming from the power that's above the variable that you are talking with or dealing with. But also, we mean by quadratics is also like the multiplication of two mixed values. So for example, as we will see down the road, but in order to make this very, very obvious for you, if I have, for example, like x squared plus y squared, this is going to be a quadratic part of a polynomial because x is up to power 2 and y is up to power 2. Even if we have within this polynomial the two mixed term like x and y, this is also considered a quadratic part of this variables. So we are seeking what we mean about quadratic parts in a polynomial is all the parts that has a power of 2. Okay? Okay, perfect. So this is the idea of quadratic forms as we can see. Of course, this is stated here, quadratic terms, a polynomial with all its terms form a power of 2 terms, even if it was a mixed terms like x squared, y squared, or even x over y. If we go for this function, for example, y equal x squared, or a polynomial of x which equal to x squared, this is considered a quadratic function because you have x to the power of what? Of 2. But for this one, if you look to this one, you will find q2, which is 1 plus x squared. This is not a quadratic form of a polynomial because you have another terms but with a power different than power 2. So this is not a quadratic form. If you look to this one for R2, Q3, R2 into R, this function is given by 2x squared for xy minus y squared. If you remark, the three terms will have a power of 2. Even the mixed term, which is x to the power of 1, y to the power of 1, multiplying them together, you will end up having a power of 2. So this is considered also a quadratic form. If you look to this problem or this polynomial in specific, you will find x, which actually plans or the image will be r, and it's mapping r3 into r, x squared, 3xy, 4xz, but you will have the term which is x, y, and z with a total power of 3, so it's not considered a quadratic function. Do you understand what I'm saying? Or a quadratic form of this polynomial. This is mainly what we are interested in if we are dealing in R3 or R2. So the definition of a quadratic form is simply is the part of the polynomial that have a total power of 2, either coming from one variable, two variables, or even a mixed variables. But if it exceeds then this and then that power, or less than that power, it's not going to be considered as a quadratic form. This is obvious. We already did go through this one. But what about this function? If you take a look for this function from the first look, it's not going to be easy to determine. But remark, if you make a simplification for this function, maybe you will be able to determine if it was a quadratic form or not. So if we look to the example of Q5, which is simply it's ln of an e to the power of x squared times y to the power of 6 plus x to the power of 6 plus x to the power of 2, and this is plus y times y plus a square root for z the power of 4, and all of this is also divided by y6 plus x to the power of 4 and plus 1. If you look from the first look to this problem, you can't give a good judgment about this function if it is a quadratic form or not. But try to simplify it. So if we try to simplify this function or this polynomial, you will remark that ln e to the power, it's exactly like writing x squared y to the power of 6 plus x to the power of 6 plus x squared, for example, which is divided by y to the power of 6 plus x to the power of 4 plus 1. Of course, you know, yes, you are right, this is going to be ln e, so I'm taking the power outside the logarithmic function. You know that ln e all together, it's equal to 1, so this is only the one that you will have. And also here you find y squared, because multiplying two multiplies in each other, you will end up having y squared. Also, you have square root for z power 4, which is going to come up out of this square root to have z power 2. So this term, it has a second degree, and this one too, also a second degree, or a degree up to 2. And if you look to this rational function, or rational part in specific, you will find this Q5. If we can take, I believe, x2 as a common, so taking x2 as a common, you will end up having y to the power of 6, am I right? X to the power of 4 and plus 1. And all of them are divided by y to the power of 6 plus x to the power of 4 plus 1. And this is plus y squared and z squared. This is why you will end up having x squared plus y squared plus z squared, which is considered a quadratic form. Are you with me? So just a simple manipulation and trying to simplify things a little bit, you will end up having a quadratic form. Which means that maybe I will give you something, it will need simplification from you, just taking advantage from this point, just to decrease the shape, and you will be able to say if, or to determine if it was a quadratic function or not. Okay, we're really interested in the sign of quadratic forms. So we will have a classification about this part, and we will continue with the details of how to analyze quadratic forms, how to get the details of the sign relative to quadratic forms. So a quadratic form is just a part, or a part of a polynomial from Rn into R has at least one of the following classification regarding the sign. I will usually use OB for optimization problems. We are interested in the sign and the image of QF, it's an abbreviation for quadratic form. The image of a QF can have an argument with no independent term. This is what we did go through Once we saw 1 plus x squared, it was not a quadratic form, because as you can see, it has two terms. One of them, the power is 1, and the other one is a free number, okay? So it doesn't have an independent variable, okay? And once you have an independent variable, which will lead to at least one image with a null vector. So one of the images of this function, it will end up having a null vector. So it's not going to be a quadratic form. We are interested about the sign of the quadratic forms only. Okay, the first of them is a positive definite. We can classify the quadratic forms as a positive definite. How to classify it, or to state if it was a positive definite or some or not? Simply by looking to the coefficients in front of the quadratic terms. So if you have a polynomial and all the coefficients of q of x is greater than 0, remark, this is going to be the shape that we are talking about. So it's going to be a positive definite function. Okay, so the coefficient of x squared, y squared are all positive. In this manner, we will have a positive definite function. Now, if you want to talk about positive semi-definite, it's going to be exactly the same, but maybe one of the coefficients of the x to the power of 2, right, the variables that exist, may equal to 0. And in this manner, we will have a positive semi-definite. Remark about the abbreviation. This is positive definite. When we write PSD, it's a positive semi-definite, which means one of the quadratics or one of the quadratic variables, it has a coefficient equal to 0. I will give you an example shortly. So the coefficient of x squared, y squared are not negative. Why we said it is not negative? It means we allow that these coefficients may be positive or 0. Do you understand what I'm saying? Okay, so the first one, it's a condition that all the coefficients must be positive, so greater than 0. For the second coefficient, for the second condition to have a positive semi-definite, okay, is one of them is equal to 0. Remark, all the positive definite are also positive semi-definite because it's already involved in this inequality. So once more, all the positive definite are also positive semi-definites. This is one, and from once we say that it's a positive definite, it means it's also positive semi-definite because it's greater than 0. But the converse is not okay. Okay, for negative definite, this is very simple classification. Once you able to do this classification method, this is the easiest of them, just by looking to the coefficients of the quadratics that exist in your polynomial. So it has x squared, y squared, z squared, without the appearance of the mixed terms. Once the mixed terms starts to appear, we will have just to think or to take extra precautions, okay? But in the case of having all the coefficients in your quadratic function is less than 0, it's going to be negative definite. And exactly the same, if one of them is 0, so it's going to be a negative semi-definite quadratic function, okay? Or quadratic form. Once more, we mean by negative definite that all the coefficients of x squared and y squared are negative values. But for negative semi-definite, the coefficients of x squared and y squared are non-positive, which means you allow the appearance of 0, and the same statements that we already had previously will be with you. What happens if we have a mixed sign for these quadratic forms? So if I have x squared and y squared, and there is a mix in the sign between them, then we will have an indefinite quadratic form. The definition of positive definite, semi-positive definite, negative definite, it will help me down the road to determine the type of optimization that I'm working with. So at the time being, I'm just focusing in how to be sure about this part of a function, if it is going to be positive definite, semi-definite, negative definite. This is really very important, okay? Let's take some examples. First of all, this slide summarizes all what we did go through. So once more, remember, if all the coefficients are greater than 0, you will have a positive definite. If some of them equal to 0, then and the rest is positive, which means non-negative values, you will have a positive semi-definite. Exactly in a similar manner, if all the coefficients are negative, you will have negative definite. If any of them equal to 0, you will have a negative semi-definite. If you have a mixed one, as I told you, you will have indefinite function or indefinite quadratic form. Some examples, for example, for this one, it's going mapping from R2 into R, okay? And you have 2x squared plus 3y squared. If you remark about the sign of these, of the coefficients of these quadratic terms, they are both of them greater than 0. So this function will hit 0 only when x plus x and y equal to 0. So this is gonna be a positive definite quadratic form. Okay, any questions? Okay. For the second example, if you look to the second example, it's a negative 7y squared. So once more, let's get to the coefficients of the quadratics. Are they all exist here? No. What's the missing? We are walking from R2 into R, so we don't have x squared. It's already exists, but the coefficient is equal to 0. So it's a non-positive coefficients, yes? So this is why it's gonna be a negative semi-definite. Once more, I have the coefficients which is negative, and some of them equal to 0, okay? So it's gonna be a negative semi-definite function. Remark that this function will equal to the origin or the 0, not just only at the point of 0 and 0, but it will be also at 1 and 0, 2 and 0, 3 and 0, 4 and 0, because mainly this function or this quadratic form can be written on this part. I can say that on this form. I can say Q2 is equal to 0, x squared minus 7, y squared. The existence of these two coefficients, that's what leads me to state that it's a negative semi-definite quadratic part. Okay? Now, when it's gonna hit 0, it's going to hit 0 not just only with the point of 0 and 0 of x and y. No, but it will also hit 0 when b equal 1 and 0. Stop substituting. It will be 0 times 1 and negative 7 times 0, so you will have also 0. And also, for any value of x, considering the y equal to 0. So for all the points that belongs to the x-axis. Do you understand what I'm saying? So it's going to be exactly the same at 2 and 0, negative 3 and 0, and so on, all of these points. So, all points in Q2, 1, 0, 2, 0, 3, 0 being zeros, all coefficient of terms are greater than 0. If you look to this one, for this function, which is negative x squared, negative y squared, both the signs of x squared and y squared are greater than 0. So there is no doubt about this. This is going to be a negative definite quadratic function, and it will hit 0 only when both x and y equal to zeros. So it's in the general form. So the only way to Q3 being 0 is at 0, 0. All the coefficients of Q terms are greater than 0. Remark, none of these quadratic forms have mixed terms. Yes? Do you have any mixed terms? So this is why it's really very simple just to make your decision and you are sure about it. Okay? Okay. Once you start to have mixed terms, it's going to complicate things a little bit for some forms. So some forms will be easy to deal with once you have mixed terms, and the others it's not going to be easy to deal with them when the mixed terms appear. And so I will try to look for another solution to determine the type of this quadratic function or this quadratic form. Okay, let's try this one. This is 2x squared minus 5x minus 5y squared. If you look to, there is no mixed term here, but the sign of the coefficients is different, am I right? One of them is positive and the other is negative. So simply it's going to be indefinite quadratic form. So the number q, so it will equal to 0 at 0 and 0, but still it's going to be indefinite function. If you look for Q5, It's an x squared minus 6xy plus 9y squared. So not all the coefficients of the quadratic forms are greater than 0. Am I right? If you have x and y positive, it's going to be much more simpler, okay? Because all the coefficients are greater than 0, so it's going to be a positive definite. But in this case, I will need further investigation. If you look closely to x squared minus 6y plus 9y squared, well, you are lucky for this one, because this problem, or this quadratic form, the coefficients will help you to have a perfect square. So Q5, if you remark, I have x squared minus 6 of x and y plus a 9 of a y squared, which I believe can be put on a perfect square like this. X minus 3 over y. So the first square is going to be x squared. First, second times 2, you will end up having negative 6xy. Am I right? And the last square is going to be 9y squared. If you remark for this guy, all the points will be greater, or all the values will be greater than or equal to what? To 0. Am I right? You will never have negative numbers. Okay? So this is a positive semi-definite function because it hits 0 for this value at the point 3 and 1. We could have a positive definite if all the coefficients are positive, but not all of them are positive. One of them is not positive, it's a negative one. So I'm in between. If it's gonna be an indefinite quadratic form, or maybe a semi-definite, semi-positive definite. How to be sure about this? It did work with this quadratic part to be a perfect square, so it's gonna end up having all the values greater than 0. And if you remark here for x minus 3y, it's gonna hit 0. Once x equal to 3y, it means that the points that we are seeking is 3 and 1. Once you put 3 and 1, it will end up having a 0. So it's a positive semi-definite. All what I said is already stated here. In Q5, coefficients of Q terms are greater than 0, the mix is greater than 0, but the quadratic part can be simply put on a perfect square, which ensures that the image are greater than 0. This is why I ended up with having a positive semi-definite function. See the coming example. Look at this example. I have negative x squared plus 2xy plus 2 of an xz. This is negative. And this is negative, and that's negative. But the mixed parts of this quadratic function, first of all, is it quadratic? This function quadratic? Yes, it's quadratic. What about the classification? Is it positive definite, positive semi-definite? What? Once you go through trying to determine the nature of this function, it's not going to be easy to determine. The coefficient of the quadratic terms are not enough to classify this quadratic form, so instead we will go through the concepts of linear vector. So, once more, bottom line, what we did go through is studying in depth the quadratic part of a polynomial, which will help me down the road to identify if this quadratic function is gonna be a maximization point or a minimization point, convexity, it's gonna work with me or help me out down the road in order to determine the convexity of this curve or of this function. So we need to focus for the time being on this quadratics. How to be sure about or what's the quadratics that exist in a polynomial? All the terms that have a sum of a power of equal to, either coming from just only one variable like x squared, y squared, or a mixed variables like xy, yz, zx, and so on. Okay, done with the quadratic part. Now we will talk about the classification of these quadratic functions. So we are in between, either positive negative, or positive definite, positive semi-definite, negative definite, negative semi-definite, and indefinite. The first classification is going to be really very simple, if accessible for you, depending on the quadratic function. If you have the coefficients in front of you and there is no mixed terms, it's going to be easy peasy. just to determine what's the type of this quadratic function. If they are all positive, some of them are positive and the others equal to 0. If it was a mixed condition, this is going to be very easy. But once you start having a mixed terms coming up to a power of 2, now I will have to think if I have a special case like the perfect square problem that we did go through. So all the values of this function is going to be greater than 0. So in this case, I'm sure about it's a positive semi-definite function, okay? If you have some of the results positive and negative, so it will lead you to have an indefinite type of a quadratic form. But in some cases, with the appearance of these mixed terms, we are not going to be able to do or to be sure about the nature or the classification of this quadratic form. So we will go to the linear algebra concepts. First of all, I will talk about how to form a quadratic part from a general quadratic polynomial, or how to get the matrix from this equation, okay? We did, I'm not really sure if you remember how to do this in linear algebra or not, but let's try these examples. For example, if I have, for example, Q1, which is, let's say, 2 of an x squared plus 4 of an xy plus 3y squared, something like this. If I want to put them in a matrix to get the matrix form, that's gonna help me out to know about this classification. It's gonna be really very simple. First of all, we are in R2, am I right? We are in R2, as we have x and y. So all I have to do is to write this system of equation. This is the x and y variables, which is a row matrix, one row times the number of variables, which is 2, and this is going to be multiplied by a 2 by 2 matrix, and then by the transpose of the first matrix, which is going to be x and y. So you will end up having a 2 in 1 dimension. So according to this shape of a row matrix, the square one, then a column matrix. By using these 3 matrices, I can get to the quadratic part that you can see here. How to do this? I will go first to the element 1, 1, which starts with the x and the x variables. X and x is going to be x squared. So I will take this coefficient with its sign. So it's going to be in the element 1, 1. So it's going to be 2. Then I will go for y, which is the second variable, and which appears here and there. So it's going to be the value and the sign. So if it was a negative 3, for example, so it's going to be a negative 3. And this will exist in the position of 2 and 2. What about 1 and 2 and 2 and 1? What to do in them? All I have to do simply is to look to the value of the coefficient of the mixed variables x and y. I will divide it on 2 and put the half of it on the 2 and 1 and 2 and the other half on 2 and 1. So this is going to be the matrix that I'm going to deal with in order to determine the type of the classification of this quadratic form. Are you with me? Okay, so once more. The general expression of a quadratic form, Q or N into R, may be written as a product of matrices, transpose matrices, okay? Now it will make sense once you go through it. Okay, a row matrix, here is the row matrix, okay, with the variables that Q of X depends on. Yes, exactly right. If I have Q, which is root square for xy, 3y square, I will have a row matrix with the coefficients that it will depend on them. What's the coefficient that will depend on x and y? So this is the row matrix first of all. And an n by n matrix whose entry ij is the sum of the coefficients of the terms of Q of X. This is the sum of the coefficients, okay, that exist in this quadratic form. He's talking about this 2 by 2 matrix, okay, which involve the variables ij. and X. A column matrix which results from the transpose of the first matrix, which is a row matrix. Are you with me? Okay, let's break it once more. What about this one? Q2, for example, it's 2 of a y square minus 3 y and z, and that's it. Can you give it to me? This is an R2, yes, this is an R2 quadratic form. So what's the dependent variables? The dependent variables are y and z. There is just only 2 of them. And this is going to be the 2 by 2 matrix. Remark that this is a 1 by 2, so it's going to work in multiplication with a 2 by 2, am I right? And of course, the column matrix is going to be the transpose of this row matrix, so it's going to be simply y and z. Once more, I will go for the numbers. The first variable is y, so y and y, I will go to y squared. The value is 2, am I right? Okay, for the y and z, it's a negative 3. So I'm going to divide it by 2. So it's going to be a negative 3 over 2 here and a negative 3 over 2 there. Am I right? Do you have x squared? Z squared. So the other variable coefficient already exists. It's a 0 times 0 z squared. So it's going to be a 0 for this one. Okay? So can you hit me with this one, with the cube of this one, the quadratic form and the representation of the matrices for this quadratic one? First of all, what are the dependent variables? So it's an x, y, and z. And this is a 3 by 1. So we will need a 3 by 3 matrix. Am I right? And the transpose is going to be x, y, and z. So once more, this is x, y, and z. I will go for x times x, which is x squared. The coefficient simply is going to be negative 1. Are you with me, Dina? So it's going to be a negative 1. And for negative 3y squared, I will go for 2 and 2. So it's going to be a negative 3y squared. So this is done, and that's done. And also I have negative z squared. So I will go to the 3 by 3 element, and it's going to be a negative 1. So now I'm done with the diagonal elements. Now once more, remark. This is the first, okay, this is the simplest way. First, second, and third dependent variable. So once we go 1 and 2, I'm talking about the elements 1, 2, and 2 and 1. So for the xy component, what's the value in front of the coefficient in front of xy component? Dina. 2 divided by 2, so it's going to be, so it's going to be in 1 and 2 and 2 and 1. What's 1 and 2 and 2 and 1? So it's going to be simply here and there. Okay, once more. xz, we are talking about 1, 3, and 3 and 1. xz, what's the coefficient of x and z? Which is 2. Also divided by 2, so it's going to be a 1 and a 1. And then I will go through y and z, which is 2, 3, and 3, 2. 2, second row, third column. I'm talking about this guy. So I'm going to look now for y and z. Y and z is going to be negative 2 divided by 2, so it's going to come up to negative 1. So this is going to be negative 1 and a negative 1. This is the matrix that I'm going to use in order to determine the classification of my function in a general case if it was positive definite, semi-definite, negative definite, semi-definite, negative definite, or indefinite. So exactly as we did go through once more, these are the coefficients: negative 1x squared, 2xy, 2xz, minus 3y squared, minus 2yz, minus 1z squared. I will start with x, y, and z, which is the row matrix with all the dependent variables. That's the square matrix n by n, and that's the column matrix, which is the transpose of the first one. Are you with me? Okay, perfect. Any questions about how to formulate this matrix? This is very major and important. Okay, so now it's an x transpose, which is the row one, a times x, or vice versa, x a times x transpose. Done. Okay, This symmetric matrix will help us in classifying these quadratic forms by the use of the previous information studied previously in linear algebra. How it's going to help me out? The simplest manner is to get the values of the eigenvalues relative to this symmetric matrix. Do you remember how to get eigenvalues? Okay, now I will talk with you about the eigenvalues of a matrix and how to evaluate them. Hopefully you will be able to remember all of this. Don't worry, I will go with you with the details of how to evaluate this eigenvalue. The eigenvalue issue is very, very simple. If you are in good control in evaluating the eigenvalues, this is one of the best methods in order to classify your problem once you have mixed variables and it's not working from the coefficients. Do you understand what I'm saying? Okay, very good. All eigenvalues of a symmetric matrix are real and with equal algebraic and geometric multiplicity. Do you remember hitting a bell? What's the algebraic multiplicity and the geometric multiplicity of an eigenvalue? Okay, the algebraic multiplicity, it means the repetition of this eigenvalue. Sometimes when I'm evaluating the eigenvalues, I will have a value that's repeated. So in this house, for example, if lambda equal to 2 times, this is going to have an algebraic multiplicity of 2. If lambda is equal to 3, but it's repeated 3 times, it will have an algebraic multiplicity of 3. Relative to each eigenvalue, there is what's called an eigenvector. Depending on the degrees of freedom of this eigenvector, we will get the geometric multiplicity. If both of them equal to each other, so the number of repetition equal to the number of free variables or the in the eigenvector that's related to this function, or the vector space related to the vector, the eigenspace related to this eigenvalue, then they will be equal to each other. We will go through this, so don't worry. So first of all, if you have all the lambdas are real and the algebraic and geometric multiplicity is equal, that's all these matrices are diagonalizable. So this symmetric matrix will be diagonalizable matrix. What we mean about diagonalization is